Imagine you are standing on the edge of the Dardanelles Strait, looking out over a violently churning, incredibly deep waterway that has aggressively separated the continents of Europe and Asia for millions of years. For centuries, this deep blue abyss was considered an absolute, uncompromising impossibility for civil engineering. The winds here are legendary, unpredictable, and fiercely aggressive. The currents below the surface are a violent, chaotic war zone of opposing flows created by the massive exchange of water between the Mediterranean and the Black Sea. To make matters even more terrifying for structural engineers, this narrow bottleneck is one of the busiest, most heavily trafficked maritime shipping lanes on the planet. Massive international supertankers, heavy cargo ships, and military vessels constantly tear through this channel day and night. You cannot build standard bridge pillars here. They would instantly become a fatal hazard for maritime traffic, or the violent ocean currents would simply rip them apart at the foundation. But Turkey refused to bow to the geographical arrogance of this strait. They decided to execute a masterclass in extreme engineering, launching a multi-billion-dollar assault to construct the 1915 Çanakkale Bridge. This was not just a transportation project designed to connect two shores. This was a deliberate, highly calculated attempt to completely shatter the absolute limits of human engineering and modern physics. The mandate they set was terrifying: construct the longest suspension bridge main span in the entire history of human civilization. To safely clear the massive shipping lanes and avoid the deepest, most treacherous parts of the strait, the central span had to stretch an incomprehensible 2,023 meters. That is over 2 entire kilometers of empty, violent air, completely suspended without a single pillar of support in between. This is a distance so unbelievably colossal that if you stand at the base of one tower and look across, the massive steel structure on the other side physically begins to disappear into the atmospheric haze. Japan's Akashi Kaikyo Bridge held the ultimate record for decades, but the Çanakkale Bridge aggressively dethroned it, demanding a level of material science, aerodynamic perfection, and sheer structural arrogance that had never been attempted before on this planet. Before a single piece of steel could climb into the sky, engineers had to win a brutal, high-stakes war deep underwater. You cannot suspend millions of tons of high-tensile steel over a 2-kilometer void without a foundation that is permanently, unyieldingly locked into the solid bedrock of the Earth. But the Dardanelles Strait does not offer a peaceful, flat seabed. The water here is deep, violently fast, and the seabed is constantly shifting under the immense kinetic pressure of the currents. Standard concrete pouring was an absolute impossibility. The aggressive underwater currents would instantly and violently wash the liquid concrete away before it could ever begin to cure. To solve this apocalyptic foundation crisis, engineers launched an unprecedented maritime manufacturing operation. On the dry shores, they constructed colossal, brutalist concrete leviathans known as caissons. These were not mere blocks of cement. They were hollow, heavily reinforced concrete fortresses, each the size of an entire city block and weighing over 65,000 metric tons. Constructing these massive structures required tens of thousands of cubic meters of specialized, ultra-dense marine concrete, heavily reinforced with a dense, impenetrable cage of thick steel rebar, specifically engineered to resist a century of aggressive saltwater corrosion. Once these massive concrete monsters were fully cured and structurally verified in the dry dock, the real terror began. The massive dry dock was intentionally flooded, and fleets of high-powered industrial tugboats hooked their heavy tow lines onto the floating concrete mountains. Towing a 65,000-ton concrete skyscraper through the violent, unpredictable cross-currents of the open strait required absolute cybernetic precision. A coordinated fleet of tugboats, guided by military-grade GPS and advanced dynamic positioning systems, dragged the colossal structures inch by agonizing inch into the exact mathematical center of the raging waterway. Once perfectly positioned over the pre-dredged, perfectly leveled deep-sea foundation bed, the engineers executed the point of no return. Massive, heavy-duty industrial dewatering and flooding pumps were violently engaged, intentionally pumping thousands of tons of heavy seawater directly into the hollow internal chambers of the massive concrete caissons, destroying their buoyancy. Slowly, brutally, and with terrifying kinetic weight, the colossal 65,000-ton structures began to sink into the dark, churning abyss. This was a zero margin for error ballet of heavy industrial machinery operating under extreme fluid dynamics. As the massive blocks descended through the violent currents, specialized acoustic sensors, laser transponders, and deep-sea robotic submersibles continuously monitored their three-dimensional vectors in real time. The caissons had to land perfectly flat on the crushed rock bedding 40 meters below the surface. If they landed even a fraction of a single degree off-center, the entire geometry of the mega bridge would be fatally compromised. A microscopic lean at the base of the ocean floor would exponentially translate into a massive, catastrophic structural resonance at the top of a 318-meter tower, guaranteeing that the bridge would eventually tear itself apart under its own immense kinetic weight. The engineers successfully weaponized shear gravity, violently slamming the massive concrete blocks into the bedrock with a heavy, unyielding impact that sent shockwaves through the deep seabed. To lock them permanently into place, colossal steel piles, measuring over 2 meters in diameter, were violently hammered deep into the earth directly through the base of the caissons, permanently pinning the concrete leviathans to the tectonic crust of the planet. With the deep-sea foundation permanently secured and heavily armored against the violent currents, the structural engineering battalions launched a terrifying vertical assault into the sky. From the submerged concrete bases, colossal steel towers began to aggressively climb upward, reaching an astonishing, vertigo-inducing height of 318 meters above sea level. These towers are significantly taller than the Eiffel Tower, but unlike a passive monument, these steel monoliths have to constantly, dynamically support the crushing, immense kinetic load of the longest bridge deck in human history. Building a structure this incredibly massive in the middle of a violent oceanic wind tunnel is an absolute engineering nightmare, as the massive steel tower blocks, each weighing hundreds of tons, were hoisted hundreds of meters into the thin air by specialized heavy-duty climbing tower cranes. The violent wind shear of the Dardanelles constantly threatened to tear the heavy steel directly out of the sky. The wind here acts like a massive, invisible, high-speed hydraulic press, constantly pushing against the towers with terrifying aerodynamic force. If the towers were built as solid steel walls, they would act like massive sails, and the extreme wind pressure would instantly cause the steel to violently buckle and snap under the incredible torsion. To neutralize this fatal atmospheric threat, the structural engineers designed the towers with a highly specific, aggressively tested aerodynamic profile. The massive steel legs are completely hollow, heavily cross-braced, and intricately angled, dynamically allowing the violent storm winds to aggressively rush through the structure rather than pushing against it. Specialized teams of deep welders and structural bolters worked in terrifying, freezing conditions, suspended over 300 meters in the empty sky. They aggressively bolted together massive steel panels with heavy industrial impact wrenches, constantly fighting against intense vertigo, sub-zero wind chills, and violent swaying, ensuring every single arm-sized steel bolt was torqued to absolute flawless mathematical perfection. But the towering red and white steel monoliths are only the rigid skeleton. The true terrifying masterpiece of the 1915 Çanakkale Bridge is its central nervous system, the massive main suspension cables. The entire mind-bending weight of the 2-kilometer steel highway deck, combined with the extreme kinetic weight of thousands of heavy commercial trucks and vehicles, is entirely held up by just 2 colossal main cables draping elegantly between the massive 318-meter towers. These are not standard ropes or typical steel wires. They are brutalist, unyielding arteries of ultra-high tensile steel, custom engineered to fight gravity on a scale never before attempted. Because a finished cable of this massive magnitude is far too heavy for any crane on Earth to lift, engineers had to utilize a highly dangerous, incredibly complex high-altitude process known as aerial spinning. They did not lift the cables. They manufactured them strand by strand directly in the sky. First, they deployed narrow, terrifyingly exposed wire mesh catwalks, draped loosely between the massive towers. Workers in heavy safety gear walked out over the 2-kilometer void, with nothing but a thin metal grate separating them from the violent, roaring ocean hundreds of meters below. Then, automated spinning wheels began aggressively pulling incredibly thin, highly refined steel wires back and forth across the terrifying 2-kilometer gap, running continuously day and night at high speeds. The sheer scale of this wire spinning operation is mathematically incomprehensible. The automated machines relentlessly pulled wire after wire, day after day, until the bridge contained over 162,000 kilometers of high-tensile steel wire. If you were to take every single strand of wire from this one specific bridge and lay it out end to end, it would aggressively wrap around the entire circumference of the planet Earth 4 complete times. Once the thousands of individual wires were draped across the void, heavy hydraulic compactors were deployed on the terrifying high-altitude catwalks. These massive, heavy-duty machines violently squeezed and compressed the thousands of loose wires into a single, incredibly dense, solid steel cable measuring nearly a meter thick. Every single one of those microscopic wires had to be under the exact, precise mathematical tension. If even a handful of wires were slightly loose, or if the extreme high-altitude wind caused them to tangle during the high-speed spinning process, the kinetic stress would not distribute evenly across the span. The tension would aggressively multiply on the remaining tight wires, causing them to violently snap one by one like high-powered gunshots, leading to a massive explosive chain reaction that would instantly sever the main cable and send the entire multi-billion-dollar leviathan crashing violently into the Dardanelles below. The engineers executed this aerial spinning process with absolute zero-tolerance perfection, wrapping the final massive cables in heavy, airtight protective wire and injecting them with specialized anti-corrosive chemicals to ensure they remained completely impenetrable to the aggressive saltwater atmosphere for well over a century. With the massive, unyielding steel arteries fully secured and permanently locked into colossal concrete anchorages buried deep inside both the European and Asian continents, the final, nail-biting climax of this extreme engineering war was the installation of the massive highway deck itself. In a standard, shorter suspension bridge, engineers might build a solid, flat concrete or steel deck, but over a terrifying 2-kilometer void, a solid deck is a fatal aerodynamic flaw. The extreme storm winds of the Dardanelles would violently catch a solid deck like a massive airplane wing, creating intense aerodynamic lift and violent torsional twisting. This catastrophic phenomenon, known in physics as aeroelastic flutter, is the exact same violent resonant force that famously tore the Tacoma Narrows Bridge to shreds in 1940. To completely guarantee that this megastructure would never suffer the same catastrophic fate, the engineers designed a highly advanced, aggressively aerodynamic twin-box girder deck. Instead of one massive, wide piece of steel, the highway is actually split completely down the middle. There is a massive, 3-meter-wide open air gap running the entire length of the bridge between the two directions of traffic. This brutalist, highly calculated design intentionally destroys the wind's aerodynamic lifting force. When the violent, aggressive storm winds slam into the side of the bridge, the immense air pressure does not build up underneath it to rip it upward. Instead, the high-speed wind violently rushes straight up through the central gap, dynamically equalizing the barometric pressure and completely neutralizing the lifting force. To actually assemble this massive, floating steel highway, colossal steel deck segments, each weighing nearly 1,000 metric tons, were prefabricated in factories on land and brought out into the violent strait on heavy marine transport barges. Massive, custom-engineered lifting gantries, suspended directly from the main cables high above in the sky, violently hoisted these colossal steel blocks hundreds of meters into the freezing air. This was a terrifying, zero-margin vertical ballet of extreme heavy lifting. The heavy lifting winches had to operate with absolute mathematical synchronicity. If a 1,000-ton block of solid steel began to aggressively swing in the violent crosswinds during the lift, it would violently smash into the delicate suspension cables, causing catastrophic structural damage to the entire system. Inch by agonizing inch, the massive steel blocks were raised from the churning water, perfectly aligned in the empty air, and then specialized structural crews aggressively welded and bolted them into the heavy vertical suspender ropes. As each massive block was successfully attached, the colossal main cables dynamically stretched and shifted, physically reacting to the immense kinetic load, forcing the engineering teams to constantly run real-time supercomputer simulations to dynamically adjust the tension and ensure the bridge's massive geometry remained flawlessly balanced throughout the entire terrifying process. Today, The 1915 Çanakkale Bridge stands as an absolute unyielding titan of human architectural and engineering ambition. It is not merely a static structure crossing a body of water. It is a living, breathing mechanical monster that constantly flexes, stretches, and dynamically fights against the relentless, unforgiving forces of gravity, deep tectonic vibration, and extreme atmospheric wind shear. It is a permanent, multi-billion-dollar testament to the sheer, uncompromising arrogance of modern human engineering. By spanning an impossible 2,023 meters across a violently churning oceanic bottleneck, Turkey did not just break a world record. They completely rewrote the mathematical limits of civil engineering. Every single microsecond of every single day, as massive commercial fleets pass safely below and thousands of heavy transport vehicles scream across the sky above, the millions of tons of high-tensile steel, colossal deep-sea concrete caissons, and microscopic structural bolts absolutely must hold their ground without failure. There is zero tolerance for microscopic metal fatigue, zero margin for aerodynamic error, and an absolute uncompromising mandate for structural perfection, proving to the entire world that with enough heavy industrial machinery, brilliant thermodynamic mathematics, and raw, uncompromising willpower, humanity can violently conquer and completely dominate the most formidable and terrifying geographical barriers on the face of the planet.